In addition to calculus-based optimization, we have another form of optimization which is known as linear programming. Here we are going to take an economic application of glassware making that will allow us to maximize the profit. But this situation will be slightly different from the usual calculus-based optimization process that we have been doing. Let us see how it will be different and how it can be helpful. Before that, this quotation can help us to understand the gist of this programming tool. It says that a problem well stated is a problem half solved. So if we explain the problem deeply, thoroughly in the beginning, it can help us to solve the problem easily because most of it will be explained already. This is a quotation from Charles Franklin Kettering, and the contributors to this tool are three. At least these are considered to be the major contributors. They are Leonid Kantorovich, George Danzig, and John von Neumann. During these years, they contributed to this programming tool. It is an alternative to the calculus-based optimization, and in this tool we use algebra and graphical figures to explain the process of optimization. Therefore, it is known as linear programming because we have linear equations. We do not consider the non-linear equations in it. For that, we have another programming which is known as non-linear programming. However, here we are dealing with linear programming only. It is basically a very applied tool because it can deal with the real life situations like allocation of the finite resources like labor, machine time, raw materials, etc. In real life, we do not just have a constraint of cost and budget. We can have multiple constraints of various kinds. So it can be the number of labor that we can hire, it can be the machine time that we can operate the machine, because we cannot operate it 24/7. We have to give it a certain time off. The factory will be closed for a certain period of time on daily basis. Labor cannot be hired 24/7, as well as raw material cannot be supplied in an infinite quantity. We will have constraints regarding that as well. So just in these three examples we can realize that the constraints, they are multiple in nature and diverse as well. So in face of multiple constraints, we can maximize the desirable variables like profits and minimize the undesirable variables like costs by using the linear programming method. Now let's talk about its process. In the process of linear programming, we will mathematize the given information into decision variables, variables that we can choose. For example, how much of the labor will be employed, how much of the machine time will be used, and how much of the raw material, for example, will be used. These are the variables that we can decide about. These are known as the decision variables. Then we have objective function. The objective function is to be optimized, that is the profit function, or we can consider the cost function for the minimization, just like we did in the calculus based optimization, where we did the differential calculus to do this kind of optimization. And there are multiple constraints in this situation of linear programming. It has some limitation, and limitation is there is only permission for linear, objective, and constraint functions. We cannot deal with the non-linear functions. For that, I already explained that we will have non-linear programming. So there are usually 3 steps, and let's do these 3 steps on an economic application of glassware making firm. Let us assume that this glassware making firm is producing a few glasswares, that is bowls and plates, which are respectively represented by X and Y. And we know that in the process of making glassware there must be some sort of processes, and these processes are mentioned here. That is, the first process is glass blowing, the second process is annealing, and the third process is the inclusion of silica sand in the chemical process of making the glassware. So they have to decide that how much of the bowls and how much of the plates should be produced in order to maximize the profit. So the first step is to mathematize the given information. We have to maximize the profit based upon the outputs, that is bowls and plates. We are informed that the profit per bowl is $150. So if I want to calculate the total profit from the bowls, I have to multiply the profit per bowl with the number of bowls that I am able to produce in this firm. So it becomes 150x. I'm also informed that the profit per plate is $100. And if it is so, I can calculate the total profit instead of the per plate profit by multiplying this per plate profit, that is $100, with the number of plates that I am producing. It will be 100y. So these are the two numbers that represent the profit from bowls and plates. For that we can add them, and if we add them we will get the total profit. This total profit is composed of the profit from bowls and the profit from the plates. This is the objective function that needs to be maximized, that is the profit from these two glasswares. Now we know that limited resources are imposing constraints, and let us see that what sort of constraints we have. The first constraint is of glass blowing time, because we know that this process or any other process in a factory or a firm cannot just happen 24/7. There has to be certain time which is allotted to each activity, and here 70 hours are allotted to the activity of glass blowing, not more than that, maybe less than that, at maximum equal to 70 hours per week, but not more than 70 hours per week. And a bowl takes 2 hours in the process of glass blowing, and a plate takes 1 hour of the process of glass blowing. So it means that 1 will be multiplied with the number of plates we produce, and 2 will be multiplied with the number of bowls we produce. And this is the time which is needed by the bowls for glass blowing. This is the time needed for plates for glass blowing. When we add these 2 points in time, it should not be greater, or at max it should be equal or less than 70 hours that are available per week. So this is the time which is consumed for glass blowing of the bowls and plates, the total time. So this is a constraint that we have represented with the help of this inequality. Similarly, annealing is another process in the making of glassware, and its total time which is possible in that firm is 130 hours. So the time that we use for annealing should be either equal or less than the 130 hours. Now this is 4x, that is 4 hours are required for the annealing process of bowl, and 1 hour is required for the annealing process of plate. So y is written here 1 into y, and 4 hours for each bowl are required for annealing process. So adding both of these times of annealing, we get the total time, which should be at max equal to 130 hours or should be less than the 130 hours. Time consumed for annealing of bowls and plates is something that we are trying to put in a constraint here. So let's talk about the third constraint, which is about the mass of silica sand that we can use in the production process. It is 45 kg. So we can use 45 kg of this silica sand, which is the available quantity, and we can use either this and that is both of them, and the mass needed for bowls will be represented by x, and the mass needed for plates will be represented by that. So this is another constraint that we have. The sum of the two quantities of silica sand that we use should be at max equal to 4 or less than 45. It's 45. Two other constraints can also emerge, and they are very simple, because production of these two physical goods cannot be negative. It means that x cannot be negative, will be non-negative, that is greater or equal to 0. And the same holds for y, that is the plates. They are also either equal to 0 or they are some number, that is some positive number. So this is a very intuitive couple of constraints, and this signifies that we are in the first quadrant because both of them are positive in this first quadrant. Now we have 5 constraints. We can put them in one table, that is the objective function and the constraints. Here you can see the objective function is mentioned. This is to be maximized. This is the function that we developed in the last step, and these were 5 constraints. These two are similar because they are non-negativity constraints, and these 3 are based on the 3 processes of production. Now we can come to the conversion of these inequalities into equalities, because it is easy to understand and diagrammatically depict equalities instead of inequalities. So we have converted them into equalities, and you will see that here as we have equalities instead of those inequalities, because we are going to convert them into lines, and that will help us to make a graph, which is an essential part of linear programming. In this process of conversion from inequality to equality, we have realized that this less than sign basically shows that the area below the curve is also possible, but above the curve is not possible, because for above the curve it will be a greater than sign, which is not happening in this case. In the second constraint, again, less than sign means that below the curve area is possible, and this less than sign also shows that below the curve area is possible, whereas we are choosing the equalities for the sake of convenience. Now these equalities can be converted into straight lines by using their x-intercepts and y-intercepts. For x-intercepts we will put y is equal to 0, and for y-intercept we will put x is equal to 0. So this part, this part, this part, this is all y, which is put equal to 0. Here x is equal to 0 again and again. So after putting these values we get various points. This point is x-intercept and this is y-intercept. If I plot these 2 points and join them, I will get a straight line showing the first constraint. If I take these 2 points and join them, I will get the second constraint's graph, which will be a straight line, and if I choose these 2 intercepts, I will get the curve or the straight line for the third constraint. Let us see that how these graphs will look like. Before we go there, just a little reminder of the fourth and the fifth constraints, which suggest non-negativity of x and y, which means that we are producing some bowls and negative production is not logical. It implies that we will remain in the first quadrant and cannot move into the third, second or fourth quadrants. Now graphing of these constraints will happen now. In this graph you will see all these constraints. You can see these 3 straight lines, primarily of the glass blowing, second is of annealing, and the third one is of silica sand. These 3 constraints, they are plotted with the help of these straight lines by using those vertices that we calculated. You can see these are the 3 x-intercepts and these are 3 y-intercepts that we have joined to come up with these straight lines. And you can see that there is a pink shade above these lines, as well as on the left hand side of the y-axis, as well as below the x-axis. All of these show that this is not a feasible region, or this is not the place where we can consider this process to happen, because this is second quadrant. Here production will not be possible. Below there will be fourth quadrant where negative production cannot be possible. And if we talk about these pink areas, it shows that above this constraint there is no possibility, because this is a constraint and we have used the sign less than or equal. It means that at max we can be on this line and below this line, but we cannot be above this line. For that we use this pink shade that shows the lack of possibility above this curve. This also happens here. Here again you can see that it is above this constraint, so this constraint cannot be violated. This pink shade avoids the possibility above this constraint. Here again another pink shade is there which avoids the possibility of any activity above this constraint. Now this blue area is basically showing that area which is permissible by all the constraints, because this area lies below all of the constraints and satisfies all of the constraints. Therefore it is termed as the feasible region, that is feasible from the point of view of all the constraints. And within this area one should decide and choose the most suitable outcome, because this is possible, and out of which we should choose the point where the production of X and Y, those glasswares, will give us the maximum profit. Now if we look at this area, it has a few vertices out of which we can choose one, because we should choose the point which is on the frontier of this area, so that we get the maximum output as well as the maximum of the profit. If I tentatively choose this point, it is the origin, and this origin can be one of the points just from the mathematical or diagrammatical point of view. However, when we will test it from the economic point of view of profit maximization, we will realize that this is definitely not an ideal point to choose. So the second point that we can choose is this vertex, and then there is this vertex, and then this point, and then finally this point. These are the vertices of this feasible region that we can use and substitute the values in the profit function. So after completing the second step in which we plotted all the constraints, now we are going to choose the optimum, and for that we can choose all these points and put their values into the objective function, that is the profit function, to see that which one of these combinations can give us the maximized profit. So this is 0 0 and then 0 45. This is the origin that we talked about. When we use origin as the point in the profit function, it will be equal to 0. It means that the profit is 0. Definitely when there is no production of bowl or no plate is produced, the profit cannot be there. So we definitely can drop this point. And then we can talk about 0 and 45, that is 0 bowls and only plates, that is a monomania, and 45 plates are produced. In that case we will earn the profit of 4500. And then the third point was 25 bowls and 20 plates, so we can choose this point as well, and putting its values in the profit function we get this level of profit. Then another point of bowls and plates borrowed from the frontier of the shaded feasible region. We get various levels of profit. Clearly this is the level of profit which is maximum among these 5 possibilities, which happens when we produce 25 bowls and 20 plates. So it is rational to produce 25 bowls and 20 plates, so that the profit gets maximized and we get this much of the profit. So during this process we learned how to develop the equations for linear programming, and then we made a graph by using all the constraints and the objective function, and finally we chose the optimum from that, which was done in this third step. This was the step in which we developed the diagram. This was the second step, and the first step was about handling the inequalities and converting them into equalities and drawing the straight lines from them. And finally we were able to do this process of optimization by going through all of these steps, and this was done by using an example of glassware-making. And here it was explained the situation of the example, and this was the topic of linear programming that was elaborated by using an economic application of glassware making. Thank you.